All right, well, now that we've gone over the basics of elements and isotopes, we can talk about where they all come from. So this story starts in the beginning of the universe. This is the Big Bang. So first we'll talk about what happened at the Big Bang, and we will talk about the elements that were formed during this process. And as you're reviewing this, pay special attention to why heavy elements were not formed during this time. This is a major implications for life as we know it and Earth as we know it. Okay, so the goal over the next few videos will be to sort of fill out this periodic table and figure out where the different elements come from. We get a few freebies right here. These are just artificial elements that have been made by humans in lab, but have no natural source. So these are just artificial elements. Everything else, though, comes from a natural process. And we think that this natural process began with the Big Bang 13.77 billion years ago. This age is the product of some clever radioisotope measurements that we won't actually go into for this course, but it's quite cool. So in the beginning, the best evidence that we have is that the entire universe was sort of encapsulated in this infinitely small, infinitely dense, infinitely high energy, capsule space. It's hard to really describe, but the important part is that things didn't stay that way, and that you have this explosion early on in the beginning of the universe, the Big Bang, and our universe has basically been sort of flying apart ever since. So this timeline, begins pretty quickly, and then it goes out into this period of kind of steady state, expansion of the universe over, almost 14 billion years to where we are today. Okay, but in terms of where the elements come from, most of the cool stuff happens in timescales that are shorter than this video. So after 1 second goes by, we have all of these tiny subatomic particles flying around that are sort of slowly turning into matter. And so in less than a second, all the protons, neutrons, and electrons that will ever exist have been made from even smaller particles. So after 1 second from this Big Bang, we have all the starting stuff. And then there's a couple of rules about what happens in the next 3 minutes, right? From going from subatomic particles to atoms themselves. So everything in this case can be qualified as a plasma. There's the protons and the electrons are not coupled together. Everything is just too high energy to be to stick together at this point in the first 3 minutes. Everything is moving really fast. So collisions that are not possible on Earth today are happening in the early moments of the universe. And a fraction of the particles are moving fast enough to basically fuse together for this for a nuclear fusion to take place. So, and the key part of this is that the lighter particles are moving faster than the heavy particles. You can think about this as a kind of energy balance. If you have the same amount of energy, a heavy particle will be moving less fast than a lighter particle, and so the heavy particles are less likely to fuse together than the lighter particles. Okay, so a few more rules. These are the small, the light, stable isotopes: hydrogen-1, hydrogen-2, helium-3, helium-4, lithium-6, and lithium-7. Everything else with this that has a similar nuclear mass is an unstable isotope, and most of them are going to be really, really unstable. They're only going to survive for 1 nanosecond, which is too small for them to fuse with other elements or other elements. There's 2 of these, though, that are stable enough to stick around for this kind of 3-minute time scale. The first are these free neutrons here. We talked in the last video about how neutrons tend to decay in a time scale of around 10 minutes. That's their half-life. It will convert to protons. But in the beginning, in the first 3 minutes, we're not very far into that half-life, so there's still a lot of neutrons flying around. And then we have tritium here. We talked about how tritium is an unstable isotope and decays over 12 years, but 12 years is a pretty long time compared to 3 minutes. So we can treat it as essentially a stable here. Okay, so this is the best guess at what was happening at the beginning of the universe when we have all these protons, neutrons, and electrons flying around. The protons and neutrons are flying around fast enough that they can collide and fuse together to form deuterium. So you have this 1-by-1 addition to go from nuclei to go from mass 1 to mass 2, And there's enough neutrons flying around that can jump in here to form tritium here as a mass 3. So the key part here is we're adding masses 1 by 1 by 1, and eventually we get to form helium-4 by adding another proton. This can go a couple different ways. You can have a proton flying in to form helium-3, and then a neutron flying in to form helium-4. That's also possible. But after 3 minutes, the game is over. The universe has expanded in this time, and so things have cooled. And so after 3 minutes, things aren't moving fast enough to keep this fusion going. And so instead you have these ricochets, right? Everything is still a plasma, but there's no, combination of nuclei. Things are not moving fast enough. And then, after maybe a half hour or so, most of the neutrons have decayed away. And this is kind of the way that things were for a while afterwards. For the next 300,000 years, nothing much happens. The universe continues to expand. The universe is still a glowing plasma, and as it expands, it's losing temperature. So things are cooling down ever so slightly, but it's a plasma. All the electrons are flying around. They're not with their protons yet. And what we have here is the universe is 75% hydrogen, 1/4 helium, mostly helium-4, and then there's only a tiny amount of lithium-7. And the reason here is that if we go back to our rules, there are no elements of mass 5 that are stable. So if we're adding, neutrons or protons 1 by 1 and trying to build our way up to heavier elements, we have this bottleneck at mass 5 because each the two possible isotopes, helium-5 or lithium-5, they stick around for less than a nanosecond. So they're not around long enough to keep adding 1 by 1 by 1. And that's basically why the synthesis of elements stops at the Big Bang. So the universe is a glowing plasma. This is a hydrogen plasma that has been recreated in the lab. You can see that everything is this sort of ultraviolet glowing color. This is what plasmas look like. They're kind of cool. And this is what the universe looked like for the first 300,000 years of its existence. It would have been sort of glowing purple if you could observe it, although you would have definitely burned up. It's super hot. And then, we talked about the difference between plasmas and gases and the fact that it's the fact that the electrons are flying around outside of their sort of, atomic shell that they're usually in. And so once things cool, as the universe expands, it starts to cool even more. And so these electrons that are delocalized find their home with the positively charged nuclei that are flying around of hydrogen and helium, and things will convert back to a gas phase. And that's this sort of what's sometimes called the dark ages of the early universe here. So this plasma has cooled into a gas, and so it stops glowing, and so that's where the end of light is in the universe. And there's no stars at this point, so there's no other sources of light here. So this is so things are dark. This relic of light, the last little bit of light, is still sort of at the edge of our universe, and it can still be detected, which is kind of crazy. So and this is one of the pieces of evidence for the Big Bang, is this sort of universal background radiation that's sort of at the edge of the known universe that was basically from 375,000 years after the formation of hydrogen and helium. Okay, so that's sort of the end of this video. We formed hydrogen and helium, and maybe a tiny bit of lithium, but not much else. I mean, the Big Bang is trying to form elements by going 1 by 1, and we hit mass 5 and things stop. So we need other processes to form the rest of the elements on Earth. And this is a big deal because we're missing things like carbon, like nitrogen, like oxygen. These are the elements that define living organic matter. So if we want life to be possible, we need something else to come along. Okay, so to wrap up, we described the beginning of the universe and the Big Bang, and we listed the elements that were formed during the time of the Big Bang. It's really only hydrogen and helium. Heavy elements weren't formed because there's a roadblock at mass 5. There are no stable isotopes at mass 5, and the radioactive isotopes are only around for tiny fractions of a second. So fusion couldn't happen 1 by 1, and that's where things stopped, basically.